Okay, so welcome back to another video. So which of these two numbers is bigger, 0.99 to the 99th power or 1.01 to the negative 101th power? So assuming that you were allowed to use a calculator, one can easily make the obvious comparison on which of these two numbers is bigger than the other. Assuming that if we were not allowed any sort of numerical computation device, calculators or even Wolfram Alpha or Symbol Lab, for example, how do we actually proceed a problem like this? Generally, when you're making a comparison between the two numbers and are given that restriction, you can actually use some calculus techniques, specifically when you're dealing with slopes and concavity with the derivative and the second derivative. That's actually the same example that we went over back in the video I did with comparing the square root of 2 and the third root of 3. So if you want to check that video out, it's actually in the link in the description below. So that's actually a Cambridge interview question, just a little bit of a trivia right there. But for a problem like this is generally how we actually want to take into that approach. So you'll actually see that we're going to consider a function for 1, but before we get to that, we can actually write this in a different numerical expression that's similar to that we can actually help utilize that comparison and of course use the calculus techniques that we will be needed to proceed forward with the observations that we need to foresee for that. So otherwise, nothing more to that. So let's actually just jump right in. So let's start with the left-hand side, 0.99 to the power 99th. So that actually can be written as the following. So it's 1 minus 1 divided by 100 to the power 100 minus 1. So the second one, and I'll actually call this capital A, for example. So for this, for the right-hand side, 1.01 to the power negative 101, we can write that as 1 plus 1 divided by 100, and then to the power, so negative, and then in the expression we have 100 plus 1, and I'll call this capital B. So let's actually consider the following function for f of x. So we're going to say that f of x is going to equal to the natural log of 1 subtract x divided by 100, then to the power, so actually let me write this expression a little bit better so it's in the considered part of the argument. So parentheses 1 minus x divided by 100, then to the power 100 subtract x, close that off, then subtract the natural log of 1, add this with x divided by 100, then we're going to raise this to the power, so negative, and then 100, add this with x, and then we're going to close that off as well. So let's actually, obviously we can see that we can use some logarithmic properties and move the exponent in front of the natural log, and in other words write that as the same as 100 minus x, then multiply by ln of 1 subtract x divided by 100. Then we can then subtract this, or rather that becomes a plus as we move that exponent to the front of 100, add this with x, and then multiply with the natural log of 1 plus x divided by 100, and then close that off. And so how do we actually proceed this with here? So notice that if I were to plug x equals 1 into the function, so that means I have 99, then 1 minus 1 over 100, then put that back in. So that, in other words, that actually becomes ln of 0.99 to the power 99, and then do the same thing over here, and it becomes ln of 1.01 to the power negative 101. But we notice that natural logs are actually always going to be strictly positive for 1. So this is still positive, that's positive. The natural log of these two, if we plug in 1, that's still going to be positive. Therefore, we can make the assumption and say that, well, rather the conclusion and say that f of 1 is actually strictly greater than 0. So with this assumption in hand, if we were to solve this out back into the beginning, so plugging 1 after all this, then solve with this inequality that this is strictly greater than 0, then one can see that indeed that we have that this can imply that A is strictly greater than B. But we wouldn't want to make that assumption yet, just because we don't have any numerical calculators or devices to say. It's just a sort of implication that's saying that if f of 1 is strictly greater than 0 with that assumption, solving that out, then we have that capital A is strictly greater than B. Otherwise, we can also say that A is less than B. So how do we actually proceed forward to say that this implies this? Well, this is where the calculus comes in. And so what we're going to do is with our f of x function, we're actually going to differentiate twice. So as you've been taught with calculus, we know that differentiating once will give you the slope, and then differentiating again. So the second derivative is going to give you the concavity. So with that, let's actually make that observation, see what we can come up with. So if we differentiate f of x, so let me write f prime of x, or rather, let me first write f of x and then f prime of x. Then we can actually proceed with performing those calculations. So first, f prime of x. So we have that this function over here, the f of x is written over here. So we actually have to apply, or I'll look at it over here. Let me underline it this way, so at least you know what you're exactly looking at. So from here, we can actually apply the product rule. So we have to do this twice since it's a sum of the products of the functions. But this is actually pretty straightforward to perform the product rule here, as we see that f prime of x is going to equal to negative ln of 1 minus x divided by 100. Then we add this with 100 minus x. Then we multiply, then this is performing the derivative of the natural log of 1 minus 1 over x over 100. So what that comes down is that we have this is negative 1 divided by 100, and then divided by 1 subtract x divided by 100. And then I'm going to move on to the next line over here. Then we got to perform the product rule for this section over here. What we have is that this is going to be plus the natural log of 1 plus x divided by 100. Then we have plus 100 minus, or plus x, we're at the plus now. Then we multiply with 1 divided by 100, and then this is divided by 1 plus x divided by 100. And we can actually simplify this out even further to see that if we just multiply the 100s to both the top and the bottom for 1, we actually get that the terms will cancel, and so we're left with 1 over 100, and then this will do the same thing over here. This is negative 1 over 100, combine that sum, and then they just cancel each other out, and we're just left with these natural log functions over here. So the negative ln of 1 minus x divided by 100, then we add this with the natural log of 1 plus x divided by 100. Now what I can do from here is let's actually solve for f prime of x is equal to 0. So this is actually pretty easy to do from here, that if we solve this out, we'll get that for 1, this is the natural log of 1 minus x divided by 100. Then this is equal to the natural log of 1 plus x divided by 100. Then further steps implying that we can actually take the e base of both sides. And so we have that this is going to be 1 plus x divided by 100 is equal to, well, either side doesn't matter, it's okay. So 1 minus x divided by 100. Then if we actually just solve for x out, then the ones can cancel each other out for 1, add the x over 100 to the other side, so that's basically x divided by 50 is equal to 0. Then we see that x is equal to 0. So what that means is that at x equals 0, that means the slope is going to be at 0. But do we know whether it's a maximum or a minimum yet? We don't know. And so that's where the second derivative comes in to determine that concavity of what we can make with that assumption. So now with that, let's actually take the derivative of the f prime of x. So let's actually move on to a different color for this. So f prime of x, f double prime of x. So we're basically just taking the derivative of this thing right here. So that's pretty straightforward. So we have 1 divided by 100, and then this is being divided by 1 subtract x divided by 100. Then the next thing is just take this derivative over here. So this is going to be plus 1 divided by 100, then divided by 1 plus x divided by 100. Then we've simplified this out. We have 1 divided by 100 minus x. Add this with 1 divided by 100 plus x. Now we actually simplify this out even further. We get that this is going to be 200 divided by 100 square, and then subtract x square. So what you'll notice is that if we solve for the discontinuities where it's discontinuous, then it's pretty easy to see that it's discontinuous at negative 100 and positive 100. But we're not really going to extend into that domain, because for 1, we have that f of 1 is greater than 0. So we just really want to pay attention to it's specifically at x is equal to 1, and then at x is equal to 0 that we solve for that slope where the slope is 0. So from here we can say that this is strictly greater than 0. And so what does that mean? If it's strictly greater than 0 for f double prime of x, that means it's concave up. And so with concave up, that actually means that at x is equal to 0 for our f prime of x that we solve Therefore, that means that x equals 0 is at the minimum. With all of our, everything that we've solved for so far, then we can say that when x, as I just said again, x is equal to 0, that's where the minimum is at, then it's concave of, so f double prime is strictly greater than 0, then we can say that f of 0 is equal to 0, and we can make the comparison and say that f of 1 is strictly greater than f of 0. And so what this means is that now we can plug in 0 back into our original function for f of x over here. So that means we have 100 subtract 0, then multiply by ln of 1 subtract 0 divided by 100. Add this with 100 plus 0, then ln of 1 plus 0 divided by 100. Then all this is actually just going to equal 0. So indeed, f of 1 is strictly greater than 0. Then that means we can actually go into the implication and say that a is strictly greater than b, and therefore this further implies that 0.99 to the 99th power is indeed strictly greater than 1.01 to the power negative 101. And just like that, this actually completes our proof. So therefore, in conclusion, say it again one more time, 0.99 to the 99th power is bigger than 1.01 to the negative 101 power. So just like that, there we have it. So yeah, that's pretty cool if you ask me.